So if I now continue where I left off, is that we have three equations now. We have the free equation, so the concentration of the free receptor, which is R total 1 plus 1 over S divided by Ks, 1 plus 1 plus L. We have the concentration at equilibrium of the receptor bound to the signal, which is S Ks 1 plus S Ks 1 plus L, and we have the equilibrium concentration of the active receptor, which is R total L times Ks 1 plus SKS 1 plus 1 over L. Okay. So that means we have, what have we been considering? So the receptor binds to S, and this leads to a conformational change. We assume that this concentration is fixed, so that is actually a parameter. Those concentrations vary with S, so those we have calculated under equilibrium, and there are two parameters that play a role, and that is Ks, so that is the equilibrium associated with the first reaction, and there is this coefficient L, that is the conformational change, equilibrium constant. Now what we were after is the input-output relationship. So the output is the concentration R star E, and the input is the concentration of the signal. So what we want to draw is we want to sketch this guy. So this concentration as function of the concentration of S, and while L and Ks are constant. So we need to think a little bit about the structure of these equations. So if we rewrite this, we could say, alright, so what we have R2 multiplied by a ratio. And this this ratio has S in it, and then there is this constant alpha, and alpha is L times Ks, and then there is 1 plus S divided, multiplied by 1 over Ks, 1 plus 1 over L, right? And this thing is another constant that we might as well call beta. So what we are considering, we have RT divided by S by alpha 1 plus S times beta. Okay, so we can write this out a little bit further. You can say, okay, so it's S divided by alpha plus S times alpha times beta. But whichever way you look at it, this dependency is going to be hyperbolic. Okay, and if you don't believe me, plot it in Excel and then you will see. And there's also an easy way to figure it out. Is that, so first of all, when S is 0, clearly this concentration is going to be 0. If S is infinite, so if it's really large, then the ratio is going to be 1. So there's a maximal concentration of the active receptor. We knew that already, because there is a total amount of receptors, so the active concentration cannot exceed that. And any points of the receptor concentration as function of S in between, they will fall on a hyperbolic curve. Okay? So it will always be hyperbolic, so it will never be this steep curve that was introduced earlier. Now if you would play around with these constants, that's something that you can do, for instance, in Excel or your favorite plotting software, is what you can do, you can play around with the hyperbolic curve. You can make it rise already at low concentration of S, but also at higher concentrations of S. So that all these different lines you could, for instance, compare at 50% of the total concentration of the receptor being active, and then you will see is that the concentration required to activate the receptor for 50% is different in all these cases, and this would then be, say, a lower affinity case. So here you have a low affinity receptor and here you have a high affinity receptor. So if there is a cell that needs to, say, sense a stress, and this stress is already at low concentrations very toxic, then you would require a sensing system that senses low concentrations of signal clearly, because these are the toxic situations, then there should be a response. But if you have, say, a nutrient, so you only want to grow at nutrient concentrations that are high, and you would have a sensing system for that, you would need a low affinity receptor. So this solves the problem we set out to solve, and that is to draw the input-output relationship for a sensing circuit. And here we've done it for the simplest system where you have binding and conformational change, and in the next lecture we'll look at the kinase phosphatase system. In the kinase phosphatase system, what it can do, it can give rise to the very steep input-output relationships, whereas the current system we've looked at cannot be any steeper than a hyperbolic curve. Alright, thank you.